Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 98 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, most of you guys probably already have your gear, but if you don't, look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to show you my solution to the homework assignment that I gave you in lesson number 97. Now, what was that? In lesson number 97, I showed you how to control the angular position of a servo by creating a pulse train where the width of the on pulse defines what the angle of the servo will go to. And then I demonstrated that teaching by writing just a simple Python program. But what we saw is Python is really not the way to do it, because Python is notoriously poor at accuracy in timing functions. And then also, if we're sitting there trying to very perfectly create that pulse train, then we can't do anything else. So what would this be an absolute perfect problem for? Who is our friend? The state machines. And so what your homework assignment was to be able to set the servo to a certain position based on a state machine program. Okay, I must first ask, how many of you were successful? If you were successful, leave a comment down below. I am legend, double chest bump. And if you were not successful, leave a comment down below. I folded up like a cheap Walmart lawn chair. Okay, well, enough of this talk. Let's jump in and see if we can get this thing started. And I always tell you this on any engineering project or on any program that you write, you always want to sketch it out on paper first. And that's always true, but that is really true in spades when we are dealing with something like the state machine. Why? With the state machine, we have very few commands that we can give. We have very few commands that we can give. And so oftentimes we've got to do sort of roundabout paths to our solution. So we really want to map things out first on our sketch pad. Okay, so let me do that. Let me get out of your way. Let me get a sip of coffee. And let's jump right in. So let's start by kind of reviewing what we learned last week. We learned that in order, what is this? Okay. All right. Maybe this will work now. Okay. What we learned was 1, 2, 3, 4. Okay. What we learned was that in order to control the angle of the servo, we need to be operating on a pulse train with a period of 20. So the overall period of the pulse train needs to be 20 milliseconds. So this is 0, and then we'll come and say that's 5, 10, 15, 20. And then we'll label this to make a little bit of a graph. So this is 0, 5, 10, 15, and 20 what? Milliseconds. All right. Now, what we also learned is that we're going to have a pulse in that period, and the width of the pulse is going to define what the position of the servo is. And we saw that for a pulse width of 0.5 milliseconds, we'll have 0 degrees. And for 2500 milliseconds, we will have 180 degrees. And for 1500 milliseconds, we will have 90. So for the purpose of this homework, let's just say that our goal is to set our servo to 90 degrees. So what does that mean? That means that we need a pulse width of 1.5 milliseconds. Now, I don't want to work in milliseconds. I'm going to work in microseconds just because I don't want a 0.5. I don't want a decimal value. And so everything we're going to convert to microseconds. So I'm going to start here and I'm going to come up, and that would be 1.5 milliseconds, which is going to be 1500 microseconds. And then we'll turn it off, and then we'll come over here and we'll go up again like that. So now let's look at this. What we're going to see is that our period is 20 milliseconds, which would be 20,000 microseconds. So we're going to work in microseconds. So our period is 20,000 microseconds. Period is equal to 20,000 microseconds. Now our pulse width that will give us 90 degrees, the pulse width needs to be 1.5 milliseconds, which would be equal to 1,500 microseconds. Okay, now we got to kind of think. The two numbers I need to keep track of is I need to keep track of the pulse width and I need to keep track of the period. Now we got to see as the program's running, we might be decrementing those numbers down. So I really need to save each one of those numbers in two different places. One where it's sort of stored and not monkeyed with, and then the other one where it's stored and we might be incrementing or decrementing or doing whatever to change it. But we need to have a place to permanently store the two numbers and then a place that we store them more dynamically where they might be changing. Well, what you know is that the registers that we can really deal with as far as comparing them or incrementing or decrementing or whatever are the X and Y registers. So what I'm going to do is the pulse width, that's the on time. The pulse width, I'm going to put that in the X register. Okay, it'll go in the X register. And the period, it will go in the Y register. Now, before this program is done, I might be moving those things up and moving them down, so I need a place that I can put them more permanently. So where I will save those in a way that they don't change is I will save the Y register, the period, in the ISR register, and I will save the X register, which is the pulse width, in the OSR. So these I don't change. No change. Don't mess with them. Okay? And these I can change. And then if I ever need to get the original values, I can go get it out of OSR and ISR. Okay, hopefully that makes sense. Now we're going to kind of need a strategy. Now what you might think is that you start by turning things on, and then you might count up to the pulse width, and then you might turn it off and then count all the way to the period and then start again. And that makes a lot of sense, and that's the logical way to do it. But what's the problem? We can't very easily and directly increment a register. We can only decrement a register. So where are we going to start? Because we can count down, but we can't count up. I'm going to start here at the 20 microseconds. I'm going to start here, and I'm going to start by setting the servo pin to 0. I'm going to set the servo pin to 0. Then I'm going to what? I'm going to count down. I'm going to count down until what? I'm going to count down until the X register and the Y register are the same. And when the X register and the Y register are the same, then what am I going to do? I'm going to set the servo pin to 1, and then I'm going to continue counting down. Continue counting down. So I'll just be coming across here when I get to this magic point, I'm going to turn the pulse on. And then when I get here, which is really back over here again, then I'll turn the pulse off again. So does that make sense? I hope that does make sense. Now, one of the things that we need to see is I want to do 90 degrees, and for 90 degrees, the pulse width needs to be equal to 1,500 microseconds, which I explained ad nauseum last week. So now let's think about these two registers. I'm going to have to set my period, and that is going to need to be set to 20,000. Okay, now what is 20,000 in binary? 20,000 in binary is 10011, so that's 10011, and then 10001, okay, 10001, and then 00000, and that's all one long strip. And let's see, you didn't see this. This says 20,000. 20,000 is 10011, 10001, 00001. How can you do that? You can calculate it out by hand because you understand binary, or you can use Google to just say what is the, what is the binary value of 20,000. Okay, now what's the other one that we're going to need? We're also going to need 1,500, and the 1,500, what is 1,500? 1,500 is 10111, so it's 10111, okay, 10111, and then 0110, 0110, like that. Let me make sure, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and then we need one more 0. Okay, so that's the 1,500, that's the 2,500. Now what? The 20,000 needs to go into the Y register, and the 1,500 needs to go into the X register. So that is the setup. That's how we've got to get those registers set up. Now we also need to put them not just in the X register. The 1,500 also needs to go in OSR. And then the 20,000, it needs to go in the Y register, and it needs to also go into ISR. And so that's going to be fairly straightforward to set that up in the state machine code. But now let's come in and let's think about actually coding this thing. So what we got to do is now what I want is I want 1 microsecond count cycles. I want 1 microsecond count cycles. But before I can figure out that timing, what I've got to do is kind of just write the kind of core frame or the skeleton of the program. So what I'll do is I'll have a wrap target up here. Okay. Now before I do the wrap target, I might have some of this set up to set the registers up before I do the wrap target. But just on the timing, we're going to start here with the wrap target. What did we say the first thing that we needed to do was we needed to set the pins, which will be the pin that the servo is connected to. I need to set it to a 0. All right. Then what do I need to do? I need to go get my fresh pulse width data, and I need to go get my fresh period data. So I'm going to move, every time I'm going to move to X, the OSR, and then I'm going to move to Y, the ISR, like that. I'm going to move to X, the OSR, and move to Y, the ISR. So now every time I get to this timing loop, everything is loaded fresh into the X and Y register. Now here I'm going to start my actual timing loop. So I'm going to say label, and what am I going to label? My time cycle. My time cycle. And I'll type this in a minute, but I want to sketch it out here first. Okay, then what I want to do is I just want to jump. If X is not Y to next. So this is just going to jump over this every time except when y equals x, except when y equal x. And in that case, what I'm going to do is then I would set pins to 1. So right, I'm coming across here, I'm jumping, and at this one magic spot, then I'm going to set the pins to 1. Why? Because the X and the Y register are going to be the same. Then what I'm going to do is I'm going to jump where? I'm going to jump back up here. I'm going to jump back up here, and I'm going to jump based on my period. Everything's based on the period, and that's the Y register. So I will Y decrement, okay, and then I'll jump up to time cycle like that. Okay, so I'll jump up here. Now, that will be the little thing that does this magic where we're coming across here at a 0. When we get here, we set to a 1. We stay there till we get here, and then we set it back to a 0. Okay, so this is all pretty good like this. This is all pretty good right here. And then, of course, the next thing we would do is we would have the wrap all the way back up to the top. So this would be 1 period. Okay, and then we would wrap all the way back up here to then do the next period. All right, now the one thing that we got to kind of think about here, is now our timing. So let's look at our timing. So from here to here is where we're going to be doing the timing. And how many clock cycles does it take to go through one loop? Well, the label doesn't take one because it's just a marker. It doesn't execute a clock cycle, but this will and this will. Now, it's true this will, but that one's only going to be executed one time. So on our main timing, what we're going to have is we are going to have 2 clock cycles. And if I want each time through the loop to be 1 microsecond, if I made the frequency a megahertz, then each clock cycle would be 1 microsecond. But the problem is I have 1, 2. So I better go twice as fast, which means I better operate at a frequency of 2 million hertz. Then one command would be 0.5 microseconds, and then the one loop here, the one loop would be 1 microsecond. Now, if I go through this 20,000 times, then that will be 20 milliseconds. Okay, I guess you see like that. 1 microsecond through there. So sorry you didn't see all of that. So that is really how this thing is going to work. Now, if you didn't follow me, you probably need to pause the video and go back and kind of sketch this out with me. Go back and sort of sketch it out with me to make sure that you understand it. But with that, I think we can go in and we can actually start coding at this point. I think that we can probably start coding at this point. So let's see if I... let me fire up my Thonny and get it here where you can see it nicely. I should have done this beforehand, but I got to take just a second to get my Thonny window in an appropriately visible manner to you. Okay, and I'll come back later and I'll show you the setup. Let me just show you real quickly how I have this thing set up. The orange line from the servo is going to GPIO pin 20 here. And then the power, I am powering off of GPIO pin 40 because it's GPIO pin 40 that comes off the 5 volts coming from the USB. And even though they say that you can use these SG90 servos at 3.3 volts, I find they don't always work that well. And then we are over here using physical pin 40 for the power of the 5 volts. and physical pin 38 sets up the ground rail. So the brown goes to ground, which is physical pin 38. The red goes to power, which is physical pin 40. And the orange or control signal, the orange or control signal actually goes to GPIO pin 20. Okay, but I know that sometimes I cover up my code if I use that view. So we'll come over to this for right now, which is a little cleaner view. Okay, let's see what else I need to do here. Okay, so now let's start coding. Well, I am going to, from machine, import pin, because we do still need to configure that pin. And then we're going to be using machine code, so I'll import RP2, or assembly language code. Now we are going to set up, we're going to set up the state machine. So I'm going to give a warning to Python that we have state machine code incoming, and I'm going to do that with rp2.asm_PIO. Now, you know that in a lot of the earlier lessons, we were using our pins, we were setting them as output pins, and that way we could move data to the output pins. But today we just want to set the pin. We want to set the pin to a 1, or we want to set the pin to a 0. And it's a little bit easier to configure the pins as set pins as opposed to out pins. So here, where we used to say out init, we are going to set init. And then what are we going to do? That is going to be equal to rp2.PIO dot out underscore low, and then we are going to do an out shift dir is equal to rp2 dot shift right like that. Okay, and then we close that parenthesis. Let me just look at that, see if there's anything obvious there. No, that looks pretty good. Then we will define our servo set, which will be the function that has our machine code in it. Then we'll have some lines of code. Then we will do the wrap target. And then we'll have some code, and then we'll do the wrap like that. And let's get that right. What I like to do is I like to kind of set up the skeleton for the program first, and then we'll come in later to fill everything in. But while I'm thinking of it at a high level, I want to do the things like instantiating the machine. So let's go ahead and instantiate our state machine, and I will call it state machine 0 is equal to rp2 dot state machine. And then what state machine? We're going to use state machine 0, and then servo set is our function. Then we set our frequency needs to be 2 million. So that's 2 0 0 0 0 0 0. A 2 with 6 zeros would be 2 million. And then we're going to set the base to be equal to pin. And then what pin did I say? We were going to be using pin 20, like that. Okay. And then close the instantiation. Now all we're going to do is sm0 dot active. We're going to turn the state machine on like that. Okay. So hopefully that actually works. Now, what is the challenge that we have right now? The challenge that we have right now is I need to get this big number I need to get that big number into the X register and into the OSR. I need to get that big number into I need to get it into the Y register. I need to get it into the Y register, and I need to get it into the ISR. Okay. And yeah, I need to get it into the Y register, and I need to get it into the ISR. And what is the challenge about that? With the set command, I can only set 5 bits. So I can't set a 0B10011 10001 I can't set that all at once. Okay, I can't set that all at once. So I'm going to set it in Y, and then I'm going to in it into the ISR, which shifts it in. And then when I set the next 5 and in them, it will shift them in, shift them in, shift them in, so I can populate that ISR register 5 bits at a time. Okay, so what am I going to need to do? I'm going to need to set Y, and what I'm going to need to set it to 0. Okay, I need to get back over to the code view here. I think I can go to this view now. So what am I going to need to do? What I'm going to need to do is I am going to need to set Y. I'm going to need to set Y. And what I'm going to set Y to is those first 5 bits, which is going to be the bits 1, 0, 0, 1, 1, like that. Then what am I going to do? I am going to shift them into the ISR. From Y, I'm going to get those 5 bits that I just set. Now I'm going to set Y to the next 5 bits, which would be 1, 0, 0, 0, 1. Okay, I'm going to shift those into Y, those 5 bits. Now I've got 5 more bits, but so I'm going to set Y to the next 5 bits, which is going to be the bits 1, 2, 3, 4, 5. 5 zeros. Now that number should be 20,000 now where? It is in the ISR. Okay, it is in the ISR, and that is where I want it. It's not in Y because all those little Y's were set in chunks, but where is my permanent position? My permanent position is the ISR, and that has that. Now what do I need to do? I need to do the same thing for getting the 1500 or the pulse width, and I need to get that to OSR, and with that one I'm going to be working with X and OSR. So I'm going to set, I'm going to now set X this time to 0B10111, just like I showed you. Now I need to shift that in. Now I got to think, if I shift that in, I'm going to be covering up the OSR. Okay, so really I need to do this second. So I'm going to cut. Look at what I'm doing. You see what happens? The problem is I want the ISR permanently to have what? The 20,000. But now I've got to use ISR to set X. So I would be better off cutting all of that and doing that after I do the X. Okay, so I will do all of this nonsense after I do the X. I will do the X first, and then when I come back and do the Y, it will already be an ISR. And I think you'll see what I'm talking about here in just a minute. So now I need to get into X, those 5 bits. Now I need to set X. And what do I'm going to set X to? 0B. And go back and look at your notes to see where I got these numbers from. 0, 1, 1, 1, 0, like that. And then I'm going to shift that into from X, those 5 bits. Okay, now I just need 1 0, but I'm going to go ahead and I'm going to set X to 0B 1, 2, 3, 4, 5, like that. Okay, but I just need to bring in one of those zeros. So I'm going to then say in into X. Then I'm going to get one of those. And now what should I have in X? I should have 1 0 1 1 1 0 1 1 1 0 0. Okay, and that should be 1500. Now that I have that in the ISR, I really want it where? I really want it in the OSR. So I'm going to move to OSR what was in ISR. Now why? Because I said that the pulse width is going to be saved in X and it's going to be saved in OSR. Right now I'm getting it to OSR. Now I've got a bunch of nonsense in OSR, so before I go in and start loading in the next number, I better clear out that ISR. Okay, so I'm going to clear ISR with a null. Okay, why? ISR already has all of this pulse width data in it. I want to clear that out, and then I come in and I put the 20,000 in it. So at this point, OSR has pulse width, okay, and then I'm shifting in the 20,000. So at this point, and did I set the 0B000, but I didn't bring that in, so I need to bring in that last Y 5 bits. So I left out that line of code. Okay. So now let's look at this and let's make sure that what we are doing makes sense. At this point, I have the pulse width in OSR. At this point, I have the period in ISR because I shifted it into ISR. So it is in ISR at that point. So now I am ready to move on. Now, why have not, I said that I wanted it in those two numbers in X and Y as well. Why did I not do it up at the top? Because at the start of every loop, I want to go get fresh values. So I want to get those values here. So I'm going to move to X what was in OSR. Now pulse width is both in OSR and X now. Now I'm going to move to Y what was in ISR. Okay, so OSR is keeping my pulse width permanently not changing. ISR is holding my period permanently not changing. I go out at the top of the loop and I put them in X and Y, and now we're going to be shaking and baking those numbers as we increment and decrement and jump and all of that. But at the top of every loop, which is a new period, we go out and we get the fresh values again. I hope that makes sense. Okay, I hope that makes sense. So that looks pretty good. Now we need to not wrap yet, but what are we ready to do now? What we are ready to do now is we are ready to do our main timing cycle. So I'm going to label this as my time loop. Like that. I'm going to label it as my time loop. And then what I want to do is I want to jump. I want to jump if X is, I better remember here up at the top, I need to set the pins to 0 like that. I need to set the pins to 0 because where are we? Right? Where are we? We are right here. So I need to set the pins to 0. And then now we're going to start counting down. Now we're going to start counting down. So I'm going to jump if X is not Y, I'm going to jump to just the next step. Okay, so where would next be? What is this? Okay, I gotta close this. Okay, so now where would I jump? I would just jump right here to label NXT, like that. So every time I'm going to jump over this step except the one magic point, which is the magic point, which is right here. And right at that point is the one time that I set it to 1. So then how am I going to do that? I'm going to set my pins to 1. Okay, so almost every time it is going to jump over that one, and I better close my, like that. Okay, now I'm ready to jump back up and go again. So I'm going to jump, and what am I going to do? I'm going to decrement Y. Y decrement, and then I'm going to go back up to my time loop. Okay, now remember we set this at 2 million hertz. Each command is going to cost us a half microsecond. So when I get to this timing loop, that doesn't cost a step, but this is a step. All right, the label doesn't cost anything, and this is a step. So that's 2 clock cycles, which would be 1 microsecond each time, 1 microsecond each time that we execute this loop. Now, if you really wanted to be a purist, you would say, well, you're going to do this one time. So instead of this being set to 20,000, you should set it to 19,999. But I'm just going to ignore that 1/2 microsecond in the overall scheme of this thing. I don't think the servo will mind. Okay, so there we are. And now I think what we're ready to do is we are ready to wrap all the way back up to the top. Okay, now what we see is that this loop creates one complete period. After that period is done, then you jump all the way back to the target. You reload the X register, you reload the Y register, you reset it to 0, and then you do your loop again. Does that make sense? I hope it does. Oh my goodness, is there any way that this thing is going to work? How many mistakes did I make in this, guys? I don't know if you know this, but it's not easy to do live machine coding, right? So please forgive me if I made some mistakes in here, but hopefully we'll figure them out pretty quickly. And so what we're going to do is we're going to come over to this view. And what did we do? We set that pulse width to 1500 microseconds, which should take this to 90 degrees and which should give us a pulse width of 1500 microseconds. So all eyes on the oscilloscope, all eyes on the servo, and let's see what happens here. And we're going to run it. And line 3, what, shift right? What is that? Shift right. What did I do wrong there? I made some sort of rookie mistake there. Let me come back so you can see. It says that line 3 has an error. Oh, RP2 dot PIO dot shift right. Okay, hopefully you guys caught that as well as going through it. We've done that quite a few times. So now let's run this thing, and B0001 isn't defined. What is that in line? What do we need? Hopefully you guys caught this as well. Yeah, I made some rookie mistakes here. So right here, I should have put a 0 in front of the B, should have put a 0 in front of the B. Okay, let's run it. Let's come back over here to this view. And now we're going to run it. And int object isn't callable in line 24. Yeah. Man, you know, guys, give me a break here. This is not easy. But if we look over here at line 24, it should be comma, set pins to 0 like that. Come back over here, and now we are going to run it, and boom, 90 degrees. Look at that. 90 degrees based on nothing but the state machine. And now let's see what our period is. Let's see what our period is here. We're on 5 milliseconds per division, and we have 1, 2, 3, 4. 4 divisions times 5 milliseconds would be 20 milliseconds, which would be 20,000 microseconds. Now we also want to see if this is the 1500 microseconds, so I will need to kind of expand the scale a little bit there. And let's see, like right here. And now we are on 500 microseconds per division. And we have 1, 2, 3 divisions would be 1500 microseconds. So boom, look at that. Now, I think that we could go in, and now if we wanted to go to different positions, we would just come up to this set X. We would come up to this set X, and we would try different things. Let's see if I can go back to 0 degrees. For 0 degrees, I would want 1, 1, 1, 1, 1, 0, 1, 0, 0 in this thing. So I'm going to go ahead and set that. And you guys can look up what 500 is in binary, or you can take my word for it that it is 1, 1, 1, 1, 1. And then it is, after that, it is 0, 1, 0, 1, 0, 0, I believe. And so here then, if I'm thinking of this right, I would just need to put 4. I'm going to look that up just to make sure real quick that doesn't, I just want to make sure I got that right. So I'm going to look up binary of 15, binary of 500. I want to make sure that I wrote it down right. Yeah, it's 1, 1, 1, 1, 1. And then 0, 1, 0, 0, 0, 1, 0, 0. So here then, over here, okay, so what I'm doing is I'm changing these, and so this first one is going to be changed to 1, 1, 1, 1, 1, and then this is going to be changed to 0, 1, 0, 0, and then here I just need to get 4, and then I don't need these. All right, so that should put 500 in the X. That should put 500 in the X. And now we'll come back to this view. And now we will run the thing. And then, I do need to comment out one too many line of code. I do need to move that to ISR. All right, so we'll come back over here. And we are going to run it. And boom, we went to 0. And now let's look here more closely. Let's look here more closely. Okay, and I have 1, 2, 3, 4, 5 divisions on 100 microseconds per division, 500 microseconds. Do you guys see what's happening here? The circuit is working, the math is working, the program is working, and the state machine is working. And I've kind of got the connection between all of those things where the state machine is controlling. The state machine is controlling the position of the servo. Now, what you can see is, what is the really important part of our program? The really important part of our program is the timing. And that's this part, okay? The setup up here, the setup, what you could think is that, well, why don't I just take a value, and why don't I in Python just take a value, okay? Why don't I take a value in Python and put it to the FIFO and pull it into the state machine and not have to do all of this craziness that we're doing here? Well, that would be great, but what would be the problem? You're going to mess up your timing. Like if I come here and I do like if I come in here and I do a pull and there's no data there and it waits for it or it blocks, and then I put more things in, you see, I want to keep my timing loop pristine. And that's why I set my values up here in this rather cumbersome way, okay, because I don't want to mess up my timing. But you see, what your homework for next week is going to be, let me make sure that I say it right here. What your homework for next week is going to be is, I want you to create a program where Python sweeps from 0 to 180 degrees and 180 degrees back to 0 using the state machine and using this timing. But you know, if you're sitting there just pushing, you're going to interrupt. You're going to interrupt, or putting, and pulling. You're going to interrupt this timing. So I want to show you kind of a neat little thing here. All right, I'm going to show you a neat little thing here. So what I want you to see is, like, at this point, the state machine is still running, even though my Python program has stopped, right? My Python program stopped, but the state machine is still running. And to kind of make sure that you can see that, like if I spread this out a little bit, do you see this little bit of jitter here? That little bit of jitter, you can see that that's a live signal that that thing is still running even though Python isn't running. So this is what I want you to watch. Here is some magic, okay? Now, I could issue a Python command, sm0.put, and what do I want to put? 1500. Now, if I issue that command, it is going to put 1500 where? In the TX, in the FIFO TX register. So if I do that, now 1500 is in the FIFO TX register. Okay, but what's the problem? It's not in the, and let me do it this way because I'm already at 1500. Let's say that I made it. Let me run the program again. I kind of messed that up, but let me start completely over here. Okay, so where am I? I am at 0, and so that is where I am. I am at 0. Now I'm going to do what I meant to do a while ago, which is I'm going to put 1500, which would be 90 degrees. I'm going to put that in FIFO. Nothing happens. Why? It's in FIFO. But now, if I could put it now, if I could, I just put it. What I want to do now is if I could pull it into OSR. So you might want to do something like you might want to just do a pull now, but you can't pull from Python because pull is a state machine code. So this is something very important. I can execute a state machine line of code in Python with this trick. And what is it? I am on what? State machine 0, and I want to .exec. And what is that telling? Python is sending a state machine code, and it will execute that. So watch this. I am going to, from Python, do an sm0.exec. And what do I want to execute? I want to execute a pull with the command sent from Python. And when I do that, boom, I go to 90 degrees. And so let's think about what just happened. Let's think about what just happened. Okay, when I did this, it put it in FIFO, and that doesn't change anything up here. But where I give this command, then what is going to happen, it doesn't matter where it is in the program, it is going to execute one command, and that is pull. And it is going to pull it into the OSR. And so now OSR has a new value, and it doesn't interrupt the program because this main timing loop down here, this main timing loop doesn't see that OSR changes until that loop is finished, and it goes and gets that OSR value and puts it in X. Do you see that? So let's try it again. Let's this time put an sm0.put. That is a Python command. I'm going to put 2500. Okay. Nothing happens. Why? It's in FIFO. Now what I'm going to do, I am going to do an sm0. I want you to execute this command, which is pull that. And where's it going to pull it? It is going to pull it into OSR, but it's not going to interrupt my timing because it's just going to do it and then continue the program. And then let's see what happens. boom, I go to 180. Okay, let's go back to 500. And that should go all the way back to 0. And then let's do our pull. Boom. Okay. Guys, I don't know if you are as excited as I am about this, but I am pretty excited about it. Okay. So now your homework is to make it do something like this. Okay, your homework is to make it do something like this. Rotate. Wait 5 seconds. You don't have to wait 5 seconds, but I waited 5 seconds. And then rotate back the other way. You can just go back and forth if you want. I just put a delay in there. And the reason I put a delay in there is so you could see that I can do what I want to in Python without interrupting my state machine. Okay. And if you, I'm not showing you my code because it's a homework assignment, right? I'm not showing you my code because it's a homework assignment, but I'll take the delay out and then let's run it. Okay, and there we're going from 0 to 180 and from 180 to 0. And now what I want you to see is this is looking at my pulse width that is coming off the state machine, and that thing is just going dandy as can be, right? Dandy as can be. So what is your assignment? Your assignment is to do this. All of the critical timing can be done with the code that I sort of developed today. And what was the code that I developed today? It was this is going to be kind of the heart of the program. But now what you're going to do is instead of doing all of this nonsense, you're going to replace that nonsense with those new little commands that I gave you. You're going to have to kind of figure out how it goes. Okay. Guys, I hope the homework assignment makes sense. If you guys are really, really new to state machines, it might be that this is a little bit of a challenge to you, but you guys that have really been through these 98 lessons so far, you should be able to figure it out. And if you struggle, don't get discouraged. Next week, I will show you my solution to this. Okay, guys, I hope you're having as much fun taking these classes as I am making them. As always, I want to give a shout out to you guys who are supporting me on Patreon. Right now, it is the Patreon support that allows me to continue to make these videos. If it wasn't for the Patreons, I would have to sort of, shut down the shop here, because really it's the Patreon that's keeping me in business right now. So thank you guys. You can also help me by giving me a thumbs up and leaving a comment down below. If you haven't already, subscribe to the channel. When you do, make sure you ring that bell so you'll get notification when future lessons drop. And most importantly, share this video with other people, because the world needs more people doing state machines and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.